Hi everyone, my name is Rostand Fezeu. Today I'm presenting our paper titled An In-Depth Measurement Analysis of 5G mmWave PHY Latency and its Impact on End-to-End Delay. This work was done with my colleagues here at the University of Minnesota in collaborations with Interdigital and Cisco systems. The past few years have seen a rapid commercial deployment of 5G networks. With enhanced mobile broadband services, commercial 5G deployments offer much higher bandwidth than previous generations of cellular networks. Specifically, mmWave 5G is key in supporting applications that are bandwidth intensive, like AR/VR, Ultra HD video streaming, and volumetric content delivery. Existing measurement studies have found that 5G can, in general, achieve higher throughput performance than 4G LTE. For example, with line of sight, 5G can deliver up to several gigabits per second of downlink throughput and up to hundreds of megabits per second of uplink throughput. From the perspective of new applications which require mission-critical communications, mmWave 5G is envisioned to support latency-critical application use cases like remote surgery and industrial automation. This ultra-low latency, coupled with edge computing, is anticipated to meet very strict latency requirements. For instance, the end-to-end latency requirement for self-driving cars is 10 milliseconds and 5 to 20 milliseconds for AR/VR. One way by which 5G aims to meet these strict latency deadlines is by innovating on the radio access network. It is well known in literature that wireless networks significantly contribute to the end-to-end latency, as we also show in our results. One innovation that 5G makes towards this effort is to introduce wider subcarrier spacings, flexible slot scheduling with shorter slot times. The slot time drops from 1 millisecond down to 0.125 millisecond in subcarrier spacing 15 and 120, respectively, to help further reduce the latency on the RAN and thus the end-to-end delay. 5G promises to deliver 1 millisecond or even sub-millisecond latency transfer on the 5G RAN physical link. Particularly, in 3GPP's own word, the user plane latency target on the radio interface should be 0.5 millisecond for downlink and 0.5 millisecond for uplink. Therefore, the question remains, is this target achievable given today's commercial 5G deployments? If yes, how often does this happen and in what conditions? When these conditions cannot be met, what can be done to get closer to this target? If this millisecond or sub-millisecond target cannot be reached, is this inherent of the 5G RAN architecture, which may not be easily controlled or eliminated? What factors are due to the current 5G network configurations or implementations of carrier cellular networks, which may be further improved in future 5G deployments? Before we present the main questions we pursue in this study, we want to briefly highlight some significance of this study. This study is significant for both 5G vendors and application developers. From 5G carriers, it can help them to know where to invest resources to optimize or even eliminate factors for better 5G performance. It will also help inform application developers to know where to place edge servers to meet the target end-to-end latency based on what latency is quantitatively achievable on the 5G RAN. Now that we know the significance of this study, in this slide, we clearly state the main questions we address in this study. The first question we pursue is, can today's commercial 5G deployment deliver sub-millisecond latency yet on the physical layer? We investigate factors that impact the physical layer delay and study if and how they can be controlled or even eliminated. Once we understand these factors from the 5G RAN side, we look at how server placement and sleep patterns affect end-to-end latency. For the rest of this talk, unless explicitly mentioned, all references of 5 layer refers to 5G RAN physical layer. To answer the above questions, we make the following contributions. We present an in-depth and thorough analysis which allows for the quantitative revelation of the status quo of today's mmWave 5G 5-layer delay, identifying carrier-specific configurations and poor design choices which hinders 5G's promise of sub-millisecond 5-layer delay. We study several factors that impact latency on the 5-layer and quantify them, showing that server placement decisions and UE sleep patterns can significantly impact the 5-layer delay and thus end-to-end latency. For our setup, to access the 5-layer KPIs, we use a professional tool called XCOM, which runs on a laptop connected to 4 smartphones via USB-C, as shown in the figure. XCal monitors, decodes, and deciphers messages interactions between the UE and the G node B following the 3GPP standard. To explore the benefits and impact of deploying services on the edge, we perform our latency measurements using Amazon Cloud Platform. We select 3 AWS nodes to interact with the UE as shown. An AWS wavelength WL node is the nearest edge and is directly connected to Verizon's 5G core network. An AWS local zone LZ node is the second nearest edge located in the same geographical location as the UE. Unlike WL, LZ is not directly connected to the Verizon's 5G core network. And we lastly select an AWS regional RG node, which is furthest away from the UE, but is also located in the same geographical region as the UE. With this setup and methodology, we judicially select 2 urban areas in 2 densely populated large metropolitan cities in the US and conduct measurements to capture and analyze the 5G layer KPIs like channel quality indicators, handovers, number of retransmissions, and the UE radio sleep cycle to quantify various latencies. In this slide, we start by sharing our results to the first question. Can today's mmWave 5G deliver millisecond latency yet? To answer this question, we aim to quantify the PHY layer latency in the best case. We define PHY as the time taken to send a ping echo reply in the uplink and receive the corresponding echo reply in the downlink on the physical layer. We also define the best case as the UE is stationary in RRC connected state and facing a 5G base station. This is because the channel conditions CQI values are greater than 12, which indicates higher modulation coding schemes. Our results show that in the best case, today's PHY delay scale can be as low as 0.85 milliseconds and as high as 3.08 milliseconds. Interestingly, only 4.43% of all our data samples have delays less than 1 millisecond. In other words, sub-millisecond latency occurs only about less than 5% of the time. A breakdown of the best case PHY delay into the control and data overhead showed that the control overhead is on average 3.78 times more than the data overhead. Thus, it is clear that today's mmWave 5G latency is far from enabling latency critical applications based on the 3GPP sub-millisecond latency target. These results imply that sub-millisecond PHY transmissions is indeed achievable in today's commercial 5G networks. However, this minimum latency is limited by the uplink scheduling in the RAN and is largely dominated by the control overhead. This large control overhead dominance is as a result of the network-centric approach and cyclic fixed slot scheduling that favors downlink transmissions. In our study, we observed that both Verizon and AT&T used a fixed slot configuration pattern with 3 downlink slots followed by 1 shared slot and 1 uplink slot. We believe that our results provide 2 incentives for enhancement or perhaps protocol redesign. The first incentive is that we believe that implementing and adapting all 61 proposed slot scheduling interval configurations as per 3GPP and dynamically adapting specific slot patterns for uplink and downlink heavy transmissions for different use cases will further reduce this latency. The second incentive is for uplink-centric applications with heavy uplink traffic demands like AR. The cyclic fixed slot configuration means that the network is not aware of the UE side heavy traffic demands. Therefore, we claim that offloading some uplink functions to the UE would help cap the lion's share control overhead and further reduce latency. For example, introducing a mechanism by which a UE can signal heavy uplink traffic to the network and request it an uplink specific slot configuration might reduce this latency. Now we show our results for characterizing the cost of poor channel conditions, CQI, with retransmissions. CQI is a value from 1 to 5. As a way to quantify the impact of CQI on latency, we divide the CQI values into CQI low, CQI medium, and CQI high. We then quantify the impact of CQI with a fixed number of retransmissions. We observe that sub-millisecond PHY layer transmissions is defeated with only 1 retransmission, and an additional 2 millisecond overhead is incurred with poor channel conditions. As in 4G, 5G employs a hybrid ARC mechanism to speed up retransmissions. We find out that although the HARC process is primarily to speed up retransmissions, it may cause a potential unavoidable latency overhead. particularly when the channel conditions change very suddenly, which cause a CQI to MCS mismatch. Given this, we conclude that improving the high process can provide a remedy and perhaps eliminate the additional overhead due to more retransmissions. In the practical sense, this might call for an extensive redesign of mmWave PHY layer operations, which might favor future XG radio technologies. 5G supports connected state discontinuous reception, CDRX, for UE power management. The UE CDRX behavior is determined using several timers. The on and off timer dictates how long the UE radio must stay on and go off after sending data on the network. This might potentially cause additional delays. We found out that when the server location is further away, like in the case with the Amazon LG and RG servers, the CDRX on expires and the UE goes to sleep before the data comes back from the network. Therefore, an additional 6 milliseconds on average delay is incurred on the end-to-end latency before the UE receives the data. We argued that this additional end-to-end overhead can potentially be avoided. Without devaluing the CDRX benefits, our experiments revealed that the additional overhead due to CDRX is primarily due to the network side sleep time and fixed configurations. We claim that adapting dynamic context-aware CDRX timers may significantly reduce or perhaps even eliminate the end-to-end latency impact on the CDRX, especially in the far edge nodes. Additionally, it would be beneficial for customers with limited monetary resources, as deploying applications on the closest edge, such as Amazon wavelength servers, is very expensive. However, achieving these context CDRX timer configurations require a true 5G near radio cross-layer design, which perhaps calls for a protocol redesign. To the best of our knowledge, this approach is particularly difficult and have not yet been studied in the literature. Due to time, please refer to more results in our paper. Some limitations of our work are we are unable to account for radio resource contention caused by congestion on the tower side. Our study is also limited by ICMP ping packet. Studying other application traffic patterns and their impact on PHY latency would help identify other factors. Our work also sheds light on several research directions to explore, including the impact of additional factors, such as application traffic patterns on PHY layer and the number of users within the connected range of the 5G base station, given carrier cellular collaborations. To conclude, our study have quantitatively revealed the status quo of today's mmWave achievable PHY layer latency, identifying several factors that impact both the latency on the physical layer and the end-to-end latency. We have also investigated whether these factors can be controlled or even eliminated. With that, I say thank you for listening to me. We welcome collaborations, so please reach out, and the artifacts for our study can be found in the QR code. I'm ready to take any questions.